Hi everybody, let's do our basic circuit analysis for today. This one is not so complicated circuit, but we were use the basic background to analyze and solve problems. What you're looking for, the current flowing through R1, the current flowing through R2 and R3, and also you'll be able to find the voltage at the node A. You have the source voltage 10 volt and all resistor have resistivity is 10 ohms. In this case you have three unknowns, I1, I2. You need at least three equations. We apply the KVL, Kirchhoff voltage law, for the inner loop, loop 1. By our KVL, the voltage, the source voltage, is going to equal to voltage drop across R1 plus voltage drop across R2. And for the R1, that's going to be I1, because the current I flowing through R1 and current I1 flowing to R2. And for the outer loop, the bigger one, you have the source voltage drop across R1 plus the voltage drop across R3 and the current flowing through R3, that's the I2. And the third equation that you're looking for, you apply KCL or Kirchhoff circuit law. At the node A, the incoming current, the summation of the incoming current equal to the outgoing, the summation of the sum of the outgoing current. So you have I equal to I1 plus I2. Okay, we already have three equations and we're ready to solve the problem. Let's start looking for I first. So you need to get rid of I2 and I1. First, let's get rid of right I2 in the term of I and I1. So from equation 3, you have I2 equal to I minus I1. Now the next step is you still have I1. Let's get rid of I1 by have a coefficient of of I1 of two equations to be equal. So start from equation number 2. You can write the voltage in the term of I and I1 only. So you have I2 equal to I minus I1. You rearrange the term, V in the term of I and I1. Now let's take a look at the equation number 1. That's the V equal to IR1 plus I1R2. But from equation number number 6, you have the coefficient of I1, that's the R3. But from this equation, the coefficient of I1 is R2. So you make them equal. Simply multiply equation 1 by R3 and equation number 6 by R2. Okay, just about the math. Then you end up with equation 7 and equation 8. So if you add two equations together, you can get rid of I1 because they have the same coefficient, and then you end up with this equation. You can work out this by yourself. So simply plug in R1, R2, and R3. They're all equal to 10 ohms, and that's give you the current I equal to 0.767 amp. Okay. Let's see. Sorry, I just did not scan, but I just took used my phone to take pictures. Let's blow it up a little bit. Now I think it should go to okay. Alright, hold on a second. I need to follow step page by page. Okay. Now let's look for I2 and I3. Well, you can see that R2 and R3 in parallel, and the net this stands for R2 in parallel with R3 simply become R2 R3 divided by R2 plus R3, and that's give you 5 ohms. And then now easy to analyze because you have the voltage, you have R1 and R2, they are all in series. So this one you end up with R total simply equal to R1 plus R2 in parallel with R3. That's become 10 plus 5, so let's give you 15 ohms. By applying Ohm's law, I, the current flowing in the circuit, simply equal to V over R total. That's the 10 volt divided by 15 ohms. So that's give you 0.67 amps. Same as the previous one. Now you have the current 0.67 amps flowing, and then that's going to go through R2 and R3. But since R2 and R3 there have 10 ohms, this is stands. So you simply divided 0.67, by 2. That's give you about 0.333 amp. Or you can apply the current divider. Just recall, the technique. For IR2, that's the current flowing through R2. That's going to be your current divider. Start with the incoming current I, and then you multiply with R3. That's opposite of R2. You don't pick up R2, but you multiply by R3 and divide it by R2 plus R3. Similar to the voltage divider that you will see that later on. And that's give you 0.33 amps as we calculate by using R2 and R3. They are equal, so the current flowing through R2 and R3 going to be half of the current coming in the node A. So IR2 equal to IR3, and KCL, that's the Kirchhoff current law. You can check back. Incoming current have to be equal to the outgoing current. So 0.67 amp going to equal to 0.23 plus 0.23. They are equal. Alright. And the voltage at the node A at this point simply become I2R2. So that's the 3.3 volt, same as the voltage drop across R3. Okay. Now let's recall about matrix. In case you might see this one is more complicated, but if you have more unknowns, For example, you have not only I2, I2, but you have I1, I2, I3, I4, I6. You need to use the matrix to solve for all currents. Well, let's put this one as in matrix form. By Ohm's law, V equal to R or equal to Ri. So if you use the matrix R inverse to the left and to the right, you multiply. On the left, you have R inverse V. On the right, R inverse and R give you identity matrix. So that you end up with only I. And I inverse actually equal to that's why I said, like, just recall about matrix technique. R inverse equal to 1 over determinant of R multiplied by adjoint R, matrix R. And also that's the info or transverse matrix of R. The first thing you need to do, you need to set up a matrix. From 1, you have V equal to in the loop, right? You have R1I plus R2I, and this one is the outer loop. And number 3, this is the, you apply KCL, right? Incoming current equal to the summation of outgoing current, that's I1 and I2. Finally, you set our matrix from these 3 equations. So on the left you have VV0, and on the right you can see that if you work it out, let's give you 3 equations. It's going to be I R1, right? This one, and then I1 R2. Okay, and you don't have I2, so we just put 0 in here. And for the last equation, you have I, right? I1 multiplied by negative 1, you have negative I1, and I2 multiplied by negative I1, negative 1, that's give you a negative I2. And then you can solve for I equal to R inverse multiplied by V. But the pain in the neck is that you need to look for adjoint R and determinant R. Sometimes you not work on this matrix so often, so sometimes you forget. That's why you need to recall it. Let's take a look at look for determinant of R. Determinant of R, you can work out. I put this one as the element 1, 1, 1, 2, 1, 3. And this guy is going to be a cofactor of 0. So you simply, ignore parameters in first row, right? This is the first row, and the third column. So you end up with 1, 0, 1, and minus 1. That's the cofactor of 0. Same as the cofactor of R1. That's you end up with what? R2, you have 0, R3, negative 1, negative 1, and multiply by R1. And don't forget about the sign, okay? And actually this one multiplied by a negative 1 to the power of number of row plus number of column. As long as it's become the number of row and number of column end up with even number, that's give you 1. But if become an odd number, that's give you negative 1, right? For example, you have negative 1 to the power of 3, that's give you negative 1. So you have a plus, minus, and plus. And we're looking for determinant. For this one, you have 0 multiplied by minus 1, you end up with 0. So you end up with negative of negative R3, because R3 multiplied by negative 1, so you end up with R3. Okay? And your determinant is going to be your R1, R3, R2 multiplied by negative R1, negative R3. This one actually become the minus side, sorry, my mistake. So you have sorry, positive, right? This is positive side. Alright, don't get confused. So you have R1, R2, R3, they are equal 10 ohms. So you have 10 multiplied by 10, and then minus, sorry, this is minus side here, I drop it out. So you add them up, this gives you 300. That's the determinant of R. And okay, let's move on. I brought this down as there are adjoint. As I mentioned earlier, you need to consider also take into account of side. That's negative 1 to the power of number of row and number of column. This is the 1 1, right? So this is to the power of even number, so let's give you 1, positive 1, and this minus and plus. And you also pick up a determinant of our transfer element 1 1. Now you need to work out for RT. Sorry, this is supposed to be the power, not subscript. From R, you can look for transfer. You can see a drop line here. It's just you put the mirror, and it's really reflect back and forth evenly. So R2 is going to drop, replace 1, 1 going to replace R2, and negative 1 going to replace the R3, and negative 1 going to replace it by R3. So you leave element on the dot dash line, the same. So this R1, 0 and minus 1, but you need to transfer R1 replace R2. So you have R1 here and then R2 down here. Okay, and then the next step is that you need to look for R adjoint. How do you do that? So from the element 1 1, you have right here. Okay, so you draw a line, row number 1, and draw the line of the column number 1. So you end up with 0, minus 1, R3, and minus 1. And you look for determinant. That's the 0 multiplied by negative 1 give you 0, and minus negative R3. This is supposed to be a positive, sorry, my mistake again. And this is the power of negative 1 to the even number. That's give you positive and negative, positive, negative, positive. You can work on that as well. Okay, let's do one more example. For element 3, 3, right? So you have the row number 3 here, the column number 3 here. So you end up with R1, R1, R2, 0. R1, R1, R2, R0. And the determinant is going to be this one is give you 0, right? R1 multiplied by 0, and then negative R1 and R2. Now this is positive sign. I missed something here. It's supposed to be negative sign. Sorry. Yep. So that's why I have I don't know why. Sorry, make you confused. And this one it's just the part become negative side, right? Negative R1 and R2. So this actually 100, but I got it right because I have 0 right here. So 0 multiplied by anything is that give you 0. So your current is going to be your inverse and voltage matrix. Inverse, that's the 1 over summation of R, that's the 300, and you multiply your R adjunct, and then you have the voltage, 10, 10, 0. You work this out, let's give you I equal to 0 by 666, I1 equal to 0 by 333, I2 0 by 333, the same. Okay. The last thing I want to mention is about Thevenin theorem. Okay, I draw the dashed line around the source. I consider this one as the source. You have one voltage source, then you have a 2R, and this one is simply becoming broad or moderate or light, anything. What you're looking for the simple circuit, you want to simplify the circuit. You want to represent, the source sorry, by only one voltage source and only one resistor source. So we put VTH and RTH. They are all in series with the load. The way to look for VTH or Thevenin voltage is that VTH equal to V open. What does it mean, V open? V open is mean you move the load out of the circuit, or simply you have the resistance of the load infinity, right? So this is your V open right here, or the source output. Now you can apply voltage divider. You have the voltage source, you have R1, you have R2, and this is your V open. So the voltage divider, simply you divide the source voltage multiplied by R2. This is your V open, and divided by R1 plus R2. They are in series. So you have VTH equal to 5 volt. Now what about RTH? RTH is divided by V open divided by I short. What is I short? Well, you short the load, or your resistance becomes 0. Simply looking for the current flowing to R1. This is easy, right? Just apply Ohm's law. I short simply equal to Vs over R1. That's 10 over 10. That's 1 amp. So your RTH equal to V open over I short. This is the 5 volt divided by 1 amp. Let's give you 5 ohms. So finally, your equivalent Thevenin circuit is going to be like this. You have RTH 5 ohms, you have VTH 5 ohms, and your current flowing through the circuit, since all components connected in series. Simply put this is your R total. So your current equal to 5 volt divided by RTH, that's 5, and R load, that's 10. So let's give you 1 over 3, 0.33 amps. Same as we worked out at the beginning of the lectures. Okay.